Hello, this is my sixth lecture, and today we shall discuss about potential due to a dipole at r theta coordinates. R theta coordinates, r is the coordinate of position, theta is the coordinate of angle, and this is called polar coordinates. Consider this is a dipole, and here it is minus q charge and this is plus q charge. This is the midpoint O, and distance of any charge from the midpoint O is A. And now we consider a polar coordinate at r theta coordinate. This distance is r and this angle is theta, and this is the point P. Here we have to calculate the electrostatic potential. For the purpose we join PA and PB. This is PA and this is PB, and let this distance is R1 and this distance is R2, and now we draw a perpendicular line from B point on AP. Let this is C point. Since BP and CP are equal, BP is equal to CP is equal to R2. So AC is equal to AP minus PC, means R1 minus R2. This distance is R1 minus R2. This distance is R2, and this side are equal, that is equal to R2. So this is a dipole, and this is the point at polar coordinate r theta, where we shall calculate the electrostatic potential. Now in this case we consider a dipole of charge plus minus q, separation of charges 2A with midpoint O. P is a point at r theta polar coordinates. This is the brief introduction of electric dipole. Consider a dipole of charge plus minus q, separation of charges 2A with midpoint O. P is a point at r theta polar coordinates. Now we shall calculate the electrostatic potential due to this charge, and then we calculate the total potential due to plus q charge. So V2 is equal to kq upon minus q charge. V1 is equal to kq upon R1, and potential with negative sign, and potential due to plus q charge, V2 is equal to kq upon R2. because the potential due to positive charge is positive and negative charge is negative. Now, the net potential at point P, net potential at point P, V is equal to V1 plus V2 minus KQ upon R1 plus KQ upon R2. Now we can calculate or we take an LCM R1 R2 minus R2 plus R1 into KQ. KQ can be taken common, R1 R2 LCM. So we shall get V is equal to minus R2 plus R1 into KQ upon R1 R2, and finally we get the value of net potential at point P is equal to KQ R1 minus R2 upon R1 R2. This is the net potential at point P. But here we have only the value of R1 and R2 we have assumed. So we will determine the value of R1 and R2 and R1 minus R2 in terms of R and theta. So for the purpose of we consider a triangle ABC. This angle is 90 degree and this side is equal. BP is equal to CP is equal to R2 and AC is equal to this distance is equal to AP minus CP or PC R1 minus R2. So we consider in triangle ABC, if R is very much greater than R1, R is very much greater than, or this distance is very much, this angle is negligible, means angle APB is negligible. Then angle POB nearly be equal to PAB is equal to theta. If this angle is negligible, then in this case, if this angle is theta, then this angle will also be equal to theta, and it is only possible when R is very much greater than A. Since R is very much greater than A. So in triangle ABC, the value of cos theta, because in triangle ABC this angle is theta, this angle is 90, then the base upon hypotenuse, AB is hypotenuse, AC is base, so cos theta is equal to AC upon AB. AC means base upon hypotenuse, so cos theta is equal to R1 minus R2 upon AB, or R1 minus R2 is equal to 2A cos theta. So value of R1 minus R2 we have calculated, and it is 2A cos theta. Now, since R1 is greater than R and R is greater than R2, and also R1 is nearly equal to R and R is nearly equal to R2, then R1 R2 will be is equal to R square. Just we can understand this fact from an example. If we consider three numbers, 99, 100 and 101. The multiplication of this and this number is 9999 and it is nearly equal to the square of 100 means 10,000. So in this manner R1 and R2 will be is equal to R square, nearly equal to R square. So this value can be taken just as. So we have obtained the values of R1, R2 and R1 minus R2. So equation first yields V is equal to KQ 2 into the value of R1 minus R2 2a cos theta upon value of R1 R2 is R square. We know that Q into 2a is equal to electric dipole moment, and this value of V is equal to we obtain Kp cos theta upon R square. This is the expression of electrostatic potential due to a dipole at r theta polar coordinates. So this is the expression of this dipole. Now we shall determine the vector expression, and for the purpose we shall use the in vector notation V is equal to Kp cos theta. We multiplied and divide by R the above expression. So V is equal to K PR cos theta upon R cube, or in vector expression K P vector dot R vector upon R cube. This is the expression or vector expression of potential, and also we can express it just like that, K P vector dot R cap upon R square. So these are the two expressions of electrostatic potential due to dipole at a r theta polar coordinates. And now we shall discuss about the two special cases. In it, the first one is that a axial line of dipole. At axial line of dipole, we consider the dipole just like that. This is minus q, this is plus q, this is point O, and this is the axial line, point P. Means in this case, value of theta is equal to 0, and the distance from the point O is R. This distance is A, and this distance is also A. This is A, this is B, this is P point. Means we know that V is equal to Kp cos theta upon R square. This is the expression of electrostatic potential, and theta is equal to 0 at axial line. So V is equal to Kp cos 0 upon R square, means Kp upon R square. This is the electrostatic potential on axial line of dipole. Now we shall discuss about the equatorial line, and for the purpose at equatorial line, at equatorial line of dipole. At equatorial line of dipole, we know that the expression V is equal to K P cos theta upon R square, and the dipole is in this situation. This is minus q, this is plus q, this is midpoint, this distance is A, and this distance is also A. And this is the equatorial line, a perpendicular line passing through the midpoint of the dipole, and this angle is 90 degree. Here this distance is R, this point is P. Now we join these points PA and PB, and the distance between, because this angle is 90 and this angle are same, so this is an isosceles angle, and in this case PA is equal to PB. PA and PB are both are equal. Let us consider it is X, then, and the theta is equal to 90 in this case, and cos 90, we know that the value of cos 90 is 0. So V is equal to Kp cos 90 upon R square, and in this case V is equal to, the value of cos 90 is 0, so V is equal to Kp upon R square into value of cos 90 0. So potential on equatorial line is equal to 0. So these are the two cases. At axial line of dipole, the value of V is Kp upon R square, and at the equatorial line, the value of potential at R theta coordinate, where theta is equal to 90, means equatorial line, the potential is equal to 0. We can also find out the value, these results with determining the direct value of potential. Just like that, if we want to find out VA is equal to KQ upon X, this distance is X, PA is equal to, other one is VB is equal to again KQ upon X, because this is the potential due to minus Q charge, so this value is with negative sign, and net potential V is equal to VA plus VB means minus KQ upon X plus KQ upon X, and this will be is equal to 0. So this is the with this method we also calculate the value of potential. Similarly, this distance is R plus A from A point, and this distance is R minus A from B point, and if we want to calculate the value of VA is equal to minus KQ upon R plus A, and for value of VB KQ upon R minus A. Now the net potential can be calculated. V is equal to VA plus VB is equal to minus KQ upon R plus A plus KQ upon R minus A, and also we can determine the value of V is equal to R square minus A square KQ R minus A with negative sign plus R plus A with positive sign, and here is KQ. So R minus R and plus R cancel out, and the value of V of will becomes equal to KQ into 2A upon R square minus A square. If R is very much greater than A, then A square can be neglected and we can obtain the value of A square can be neglected. So we can obtain the value R square, and Q into 2A is equal to P. So we obtain the value Kp upon R square. The similar result can be obtained directly by determining the value of potential due to minus Q and plus Q charge at axial point or equatorial points, or we can calculate by V is equal to Kp cos theta upon R square by putting the value of theta is equal to 90 and theta is equal to 0.